firstly, my name is Otávio. I'm working for Collab BioRef in Portugal, and I'm going to make a presentation about gasification by talking some aspects about the technical concepts and also to analyze a case study that is being developed here in Portugal. So, first of all, I'm going to present the company to which I am working for, which is BioRef, Collaborative Laboratory for Biorefineries. This is basically a private institution devoted to the promotion and development of new biorefineries. So basically, the activities in BioRef are divided into essential strategic domains. The first one is bioenergy and renewable gases, where we can perform works about biochemical and thermochemical processes for producing new fuels, such as those for the aviation sector and also for the transportation sector and for industrial uses. And we also are focused on the use of CO2 also for the production of fuels or e-fuels. Also, there is another strategic domain, which is the sustainable bioeconomy. This domain is mainly devoted to the use of algae and lignocellulosic materials for producing new bio-based products. Moving forward, we currently are being supported by 22 associates from Portugal. From these, 10 are of academic and energy research centers located here in Portugal. And there are also another 12 associates from the private sector, with focus areas in different activities, such as waste treatment, production of fuels, transportation, and also for the development and production of new products originating from biomass. Now, our services are also diversified. We are covering a range of services from consulting works. We also develop some state-of-the-art studies. We make some market studies for the evaluation of new biorefineries, for example. And we also are interested in the integration and also stimulation of new biorefineries by developing new concepts for their construction and development. So now moving to the core theme of this presentation. First of all, I will define gasification, which is basically a conversion of biomass that is conducted at high temperatures, around 700 to 1000 Celsius degree, with the main aim of producing a gas devoted for energy applications. In this case, the difference between gasification and the traditional combustion process is focused on the use of a small amount of oxidant agents. In this case, the oxidant agents that we can employ in the process can be air, oxygen, steam, and also CO2. These are the oxidant agents that we commonly find in the literature. But compared to the combustion process, the amount of the oxidant agent is relatively small in order to produce a product gas with some calorific value that we can use further for other applications. From this process, we also obtain tars and biochars and ashes as byproducts. So these are not very relevant for the gasification. Only the product gas is the more interesting product. Here we can see some images from the tar, the liquid fraction of the gasification that we can obtain, and also char and ash that is produced after the process, which are basically the remaining solid particles that we can obtain from the process. We also can classify the reactions that are being conducted in gasification in two categories: oxidation and reduction reactions. The oxidation reactions in many times provide the thermal energy that is required to conduct the reduction reactions. And therefore, the adjustment of the oxidant agent proportion inside the process is very relevant to contribute for this balance between the oxidation and reduction reactions that are being conducted inside a gasification process. So now talking about the products and their applications. So essentially the product gas is very rich in carbon monoxide and hydrogen contents, which provide a significant lower heating value associated with the gas. The main applications of this product gas can be the generation of energy, both thermal and electric, also the production of new renewable fuels, such as, in this case, gases such as biomethane and hydrogen, and also other liquid products that cover a diversified range of fuels, in this case, methanol, ethanol, dimethyl ether, and also a Fischer-Tropsch process to produce diesel and gasoline. So basically, each of these products that we can obtain from gasification require different proportions of CO and hydrogen contents, and also the catalysts that are used in the synthesis of these fuels are also different. So basically, these are the differences between the production processes between these all of these fuels. Biochar produced as byproduct, because it has high carbon and ash contents, it eventually can be used for the production of new catalysts and construction materials. We can see some literature that validates this application for the biochars. And also tars are a liquid fraction composed of different hydrocarbons, naphthalene, benzene, and toluene, for example, which can be used for the production of new chemical products, or eventually the recovery can also be employed. And also it is possible to recirculate part of the tars that are produced after the gasification to the process itself in order to increase the content of product gas that is being produced. However, this recirculation can be performed at a certain extent in order to make the gasification process continuous and viable. After this table, okay, we can see some reactor configurations that are commonly used in gasification. Sorry. So basically, we have two versions of the fixed bed reactors. In this case, the feedstock is introduced from the top of the gasifier and moves downwards the reactor. So the fixed bed version covers two types, in this case downdraft and updraft. The difference between them is the orientation of both the oxidant agent and the feedstock. In the case of the downdraft version, we can see that in this lower zone of the gasifier, we can see that both air and feedstock circulates in the same direction, and the product gas is obtained from the bottom. While in the case of the updraft gasifier, we can see that both the feedstock and the oxidant agent, in this case air, circulate in opposite directions. So this has implications in the process and also in the products that are obtained. In the case of the downdraft version, some of advantages associated with the process are the production of low tar amounts, an undesirable product, and also it can be implemented at small scale implementation, which is very useful for the production of energy, for example, in very remote areas and in agriculture applications. However, the feedstocks must be prepared with some demanding requirements, such as the granulometry, and also they must be very well dried. In the case of the updraft gasifier, we can see that the production of tar is somewhat higher, but as an advantage, the process can admit wetter feedstocks in the reactor. We can also mention the bubbling fluidized bed gasifier, which works in a different way from the fixed bed. because inside the reactor we employ a catalytic bed composed of minerals or other inert materials. The most common are the sands, calcium oxide, and also dolomites and olivine can be used in the bed. And in this case, the feedstock is very well mixed with the inert material in order to be converted in the product gas that exits from the top of the gasifier. The turbulence inside this bed is promoted by the injection of a fast current of air, a fast stream of air that promotes the agitation and turbulence of the particles in order to promote the conversion of the feedstock in gas. In this case, the advantage of the process is a greater tolerance for different feedstocks that we can employ in the process. In this case, the requirements are not necessarily demanding because the granulometry and the moisture content can be somewhat diversified. They are not very well stringent. And the other advantage associated with this reactor is that it can be implemented at a larger scales. We also have two other reactor configurations, the intranet flow, for instance, which admits both biomass and the oxidant agent. In this case, the biomass is very well granulated in the same channel that is introduced inside the reactor. In this case, the granulated biomass are composed of fine grains in the order of 250 to 1000 micrometers, so very well fine, in order to be very well mixed with the oxidant agent. But the process implies the use of higher temperatures and pressures when compared with traditional versions of the gasifiers. In this case, the temperature can reach 1500 Celsius degree, and the pressure can be up to about 70 bar. So in this case, the product gas is very well clean and very energetic with minimal tar production. The process also has high feedstock conversion rates because of the granulated form of the biomass, but requires a very well grains, or requires a pretreatment of the biomass in order to achieve the quality of the product gas that we can reach with this process. There is also the dual fluidized bed version. In this case, we have two reactors, the combustor and the gasifier. The gasifier occurs in the traditional way. Here we can mostly use steam, is the most used oxidant agent in this version of gasifier. But we have a bed material that is being recirculated between the gasifier and the combustor. Typically, this bed material can be calcium oxide, for instance, that captures the chars and CO2 from the gasifier and move them to the combustor, where then can be released again in order to produce the flue gas, mainly composed of CO2, and also the char that is being deposited inside the combustor. Here we can use air to promote the release of CO2 at relatively high temperature when compared to the gasifier, and then the bed is moved again to the gasifier to reinitiate another cycle of conversion. The product gas is here again composed mainly by CO and hydrogen. In this case, the dual fluidized bed version only can be implemented at larger scales, and they can be very used. They are mostly used for the production, for instance, of biomethane and other biofuels that require high proportions of CO and hydrogen. And we also have another advantage associated with this process because the CO2 stream is produced separated from the typical gasification process. We can also obtain a gas composed of high hydrogen and CO contents and also with a high calorific value. Now, this table presents a summary about the syngas composition obtained from the different reactors, fluidized bed, updraft, undraft, dual fluidized bed, and intranet flow. And mostly with what we can obtain from this table, the most important conclusion perhaps is the effect of the oxidant agent in the composition of the syngas. We here can see that when we use oxygen or steam as oxidant agents, we can increase the proportion of hydrogen that is generated from the different reactors. And this is eventually very useful for the production of new synthetic fuels because we somewhat can reach better proportions between hydrogen and carbon monoxide that are required for the production of new fuels in further processes that follows the gasification process. Now, making a comparison between the advantages and disadvantages of gasification compared to the combustion, we can see that the emission of pollutants such as nitrogen and sulfur compounds are reduced in the case of gasification because we are injecting a less oxidant agent. Also, we can implement the gasification at smaller scales with high energy conversion because we are using the syngas to produce heat instead of a solid product that is typically used in combustion. So combustion of syngas is somewhat efficient in this case. And there is also a good flexibility of producing new products, energy and fuels when using the gasification. While in the case of combustion, we only obtain flue gas and thermal energy. Gasification can be also autothermal if the proportion of oxidant agent is correct. This must be very well controlled. And now some of the disadvantages are related with the requirements of the pre-treatment of feedstocks that are somewhat demanding when compared to combustion. Also, gasification presents a lower technology maturity. Combustion is very well widespread around the world and very well known. There is also a need to highly to inject the oxidant agent with very precise amounts in order to obtain a good composition for the syngas. There is somewhat instability of temperature, and also the process can be somewhat less silent and odorless when compared to combustion. Another issue that we can find in the product gas is the presence of lots of contaminants that when they are contained in high proportions, they can cause different problems in downstream equipment, such as catalyst poisoning when we are trying to synthesize new fuels with the syngas. Corrosion issues can also occur, formation of deposits, and also air pollution can be associated with these contaminants. Despite they are present in low amounts, even these lower amounts can produce significant problems in downstream equipment. And this is why we need to perform a gas cleanup step after the product gas is obtained from the gasifier. This scheme presents an example of this cleaning system, which is composed by a part devoted to the removal of solid particulates. For example, cyclones, filters, and electrostatic precipitators are some common components very well known in the market and can be used to remove these particulates. The wet scrubber, which basically the gas is mixed with water with high agitation, and the water may capture different contaminants. In this case, stars, nitrogen, and sulfur compounds can be retained by this water. Sometimes the water can be mixed with other solvents to enhance the capture of these contaminants. Then we can employ adsorption pads composed of zinc and copper materials to remove sulfur compounds. And finally, an activated carbon bed stage to fine-tune the composition of the syngas by removing other trace contaminants that were not captured in previous steps. Mostly to produce biofuels and renewable gases, The syngas must be very well cleaned with lower proportion of these contaminants in order to promote a good conversion of the gas into new fuels by using appropriate catalysts in further processes. Now, moving to the case study that we are about to present, we can mention the project High Fuel Up, currently being developed in a period of about 4 years, 2022 to 2026. In this case, the project is mainly devoted to convert low-grade feedstocks into biomethane by using dual fluid acid bed gasification associated with other processes, in this case, electrolysis and methanation with a TRL level around 6 to 7. So basically, it's a demonstrator that is being developed and funded by the Horizon Europe program. In this case, the consortium is composed by BioRef, leading the project, with the contribution of other 10 partners, Portuguese, Swiss, and also from the United Kingdom, Spain, and from Germany. So these partners will then provide technical support required for the development of this project. We also have to mention some of the innovations associated with the project High Fuel Up. First of all, is the use of different feedstocks. In this case, low-grade wastes composed of digestate from sewage sludge, and also different lignocellulosic materials obtained from crop rotation systems that we also intend to analyze and study in the project. We have a hybrid operation of the gasifier between SEG and OxySEG. SEG is an acronym of sorption enhanced gasification, a variant of a dual fluid acid bed gasifier that we will later. In this case, we use the same reactor configuration to promote the hybrid operation of the process. We also have a flexible addition of hydrogen promoted by electrolysis, and which is required for the methanation stage to produce the biomethane. And with all of these innovations, we expect to enhance the carbon conversion efficiency and also the reduction of the production of greenhouse gases when compared to traditional processes. The project is intended to be installed in a city in the center of Portugal, in this case Tondela, and it is intention also to perform a retrofit of an existing circulating fluid acid bed gasifier inside this site. So the current plant that is installed in Tondela has this aspect with the circulating fluid acid beds installed before, and we intend to improve this gasifier for the dual fluid acid bed version to convert it for biomethane production. As already referred, the feedstocks used in this case are digestate sludges and also different lignocellulosic crops with an injection until 4 tons per hour, and also with biomethane production that is expected to reach 50 meter cubic per hour of gas. Here we can see a simplified scheme of the operation of High Fuel Up project. In this case, we have a dual fluid acid bed version composed by the gasifier and the combustor, admitting biomass and steam in the gasifier and different oxidant agents inside the combustor. We also use calcium oxides between the gasifier and combustor for the carrying of CO2. So in normal uses, the CAO goes from the combustor to the gasifier, and then when the gasifier, when the CAO captures the CO2, it is transformed in CaCO3 to move back to the combustor to release the CO2 for other processes. We also can see a step composed of a gas cleaning stage both for the product gas and flue gas produced in the gasifier and the combustor, and the fluidized bed methanation that uses the hydrogen-rich syngas and CO2 to convert both gases into biomethane. Then the gases are purified and transformed into liquid biomethane mainly for the transportation sector. We also have a motor generator, which uses part of the syngas produced by the gasifier to produce electricity that is required for the operation of the plant, and therefore this minimizes the injection of electricity from the public grid. And we also have an electrolysis module that only operates in oxyseg mode. The operation between seg and oxyseg is dependent on the proportion of hydrogen to CO ratio inside the syngas. When this ratio is low, that is when the hydrogen production is low, when the hydrogen to CO is high, sorry about this error, then we mean that the hydrogen proportion is also high, and therefore we operate the plant in the seg mode. That is, we only inject air in the combustor to promote the production of CO2 required for the fluidized bed methanation process. However, the biomass can be somewhat poor, and therefore the production of hydrogen cannot, sometimes may reach low proportions. And therefore, when the H2 to CO ratio is somewhat lower, it means that we have to enhance the production of hydrogen inside the syngas. And in this case, we move to the operation in oxyseg mode. That is, we inject oxygen in the combustor to enhance the production of syngas with high hydrogen content after the gasification process. And also in the oxyseg operation, we can use the electrolysis mode that enhances the production of hydrogen required for the methanation process. And therefore, we can reach the conditions that are required for the methanation to conduct the production of biomethane by using appropriate proportions of hydrogen to CO ratios inside the syngas. Now, finally, we can mention some highlights of this work by reinforcing and highlighting that gasification in most cases can be considered as a sustainable and very flexible process to produce different products from biomass. Because of this sustainability that is proved, the European environmental policies are suitable and adequate for the gasification process, and therefore gasification can be very interesting to reach the goals established by the European Union regarding the production of renewable fuels and reduction of greenhouse gases. We also saw that the injection of both steam or oxygen can enhance the syngas composition by increasing the hydrogen and CO amounts. However, the production of both steam and oxygen requires other complexities and costs, high costs, when compared with the use of common air to the process. We also can reinforce that the gas cleanup step is very critical in the process, which requires a very thorough planning at affordable cost for the appropriate cleaning of the product gas. And we did not find many projects associated with gasification in Portugal. We can mention the High Fuel project and also another project that is being developed for a paper industry company. So there are too few projects associated with gasification, and therefore these projects must be stimulated for the development and deployment of new gasification units inside the country and eventually across Europe. So finally, I must mention the contacts of BioRef if you are interested in more information about our company, and thank you all for your attention.